Why is it me? It's always you. And then it's you.
Okay, so just to get started here, first I'm going to we're going to take a look at what the definition is, and then we'll try it on a couple points. So this is the definition. I'm going to paint a picture with an applet for you in a minute here, but this is the tangent problem here, and this is one of the definitions that you'll need to know for how we find a derivative. Now, if you copy that into your notes, this is a definition of how we find a tangent line. But it's not always the way we do it, because we'll have better techniques shortly. Oops, sorry. How we find a slope for the tangent line. Okay, so let's take a look now. I'm going to bring up an applet for you to take a look at, so you can see what this definition actually means. Okay, so here's the, whoops, wrong web spot, but anyways, let's, okay, so here's the thing that we're looking at as a tangent line. So just so everybody remembers, this is what we mean by the tangent line problem, being able to find the slope or a line that touches one part of the graph, not a secant line like you would have done in, say, grade 10. So let me just show you here where that limit comes in. So here's the applet that we're going to take a look at. Maybe we can go bigger. Yeah, that looks nice. Okay, so the first one is looking at the sine graph. How would you do that? Well, let's just say if I use this one here, let's go to the point 0. Okay, let's look for the derivative at 0. Okay, and I want to be, let's say I'm 1 unit away. Okay, so there's the secant line if I'm 1 unit away. If I shrink it some more, like say I go to a half, see that green dot keeps getting closer to the blue dot as the change in x becomes a 0. Those 2 points would be the same. So if I go 0.25, now it's even closer. And you can see as it gets closer and closer, it's actually turning into the tangent line. It's pretty hard to tell that it's not the tangent line at this point. So I'll just do one more shrinking of how far away from x I am. So say I'm at 0.001, right? At this point, graphically, we can't really make out the difference because they're so close together. But you can see that that's only touching 1 point now. And that's what the limit is trying to say, is that all this nonsense in here says, as I take the change in x, okay, so instead of being at x itself, I'm x plus some difference. So in my example, I started at 1, then I went 0.5, 0.25, and I kept going. And as I got closer and closer to 0, that was giving me a tangent line. So it comes from the point slope formula that you already know. So here's, this is the one that you already have been using. Okay. But this time the points are going to be at x and x plus delta x, that little bit that's going to be moving. So if I was to put that into the slope formula, I'd end up with f of x plus the change, which is going to become a 0. Take away f of x, and x plus delta x minus x, which of course those will cancel out, and that's why I'm only left with the delta x here. Okay. So that's one of the definitions that we're going to work with. In next block we will take a look at a different definition. So let's try and use this, see if we can figure something out. Okay, so using the definition of derivative, we would like to find the derivative at the point 2,1 for 2x minus 3. Okay. I'm going to have to erase some of this here just to give us a bit of space. But here's what we're going to do then, is we're going to use the limit process. So we're going to put in these values here. So I'm going to have the limit as delta x goes to 0. And this is my function. So it's going to be 2 times x plus delta x minus 3. And I usually put square brackets around it to remind me this is one of the functions. Take away 2x minus 3. So this is the function at x plus delta x. This is the function at x. Oops. So clearly we can't evaluate this because we divide by 0. But this is one of those instances where you can see that there's going to be a tangent line. That's a quantity that actually exists, but in order to find it algebraically, you divide by 0. So this is where the limit comes into play. The limit is a way of getting around that algebra that wouldn't work. So if I was to expand this out, I would get yeah, I guess for time's sake, I won't put, well, shouldn't be, I'll do it proper. So I have the limit as delta x goes to 0. If I expanded it out, it would be 2x plus 2 delta x minus 3. And then the other function is going to be take away 2x plus 3 all over delta x. So what happens if I collect up the like terms? Well, 2x is going to cancel out, and 3 is going to cancel out. So what I end up with is 2 delta x over delta x, which is 2. Okay. So even though that limit goes to 0, it's going to be one of those removable discontinuities, one of those problems that goes away from the algebra. And that tells me that any tangent line to the line y equals 2x minus 3 has a slope of 2. Okay, so here was the original function. Every tangent line will have a slope 2. Okay, so what I'd like you to try, and we'll talk about your answer, see if you can figure out how to come up with the, using the limit process, see if you can come up with the derivative here, and then we'll talk about what those results mean. But see if you can do the algebraic part of it, just to get started. Okay, so I'm going to try to catch up to some of you are there, some of you are still working at it. But if you use your definition of derivative that we've just talked about with the limit as delta x goes to 0, if I put it into the first expression, it's going to be x plus delta x squared plus 1. Take away x squared plus 1. And it's all over delta x. Okay, so now I have, if I expand this out a bit, I'll have the limit as delta x goes to 0. And this piece up here, if I expand it out, is going to be x squared plus 2x delta x plus delta x squared. And shoot, I'm running out of space here. Take away x squared, take away 1. And that's all going to be over delta x. So if I collected my like terms up, x squareds would go away. Oh, and I forgot a plus 1 over here. And the 1s would go away. And what I'd be left with is the limit as delta x goes to 0. And this is 2x delta x. And delta x squared. All over delta x. Okay, so now this is the way it's going to work out for us when we're trying to find a derivative, is the algebra should get us around this dividing by 0. So that means I'm going to have the limit as delta x goes to 0. So this will be gone, and I'll be left with 2x. One of these will be gone, and I'll just have a delta x. Okay, so what happens to delta x as it goes to 0? That's gone. So I'm left with 2x as my derivative. And what does it mean when we want to find the slope? We'll verify this with the picture in just a second. But if I wanted to find the slope at the point 0, 1, that's x equals 0 and y equals 1. That means I'm going to put in x equals 0 to here. The slope of the derivative is 0. Okay. At negative 1 and positive 2, the value for x is negative 1. So it's going to have a tangent. The slope will be negative 2. Okay, so we'll verify this in just a second here. The reason we didn't have to do it in the previous example was because it equaled just 2. There was no additional x or anything in there. Because if you think about the line, that line has a slope of 2. if you wanted to make the any single point has to have the same slope. So it didn't matter where we were on the graph, it's a constant. Whoops, that's the eraser. It's a constant. The slope of the derivative is always going to be 2. Nothing changes it. Whereas here, for a parabola, it's not a constant. There's an x in here. We have to put in our value for x to figure out the slope. So here's our x values that we put in. Let's verify this graphically so you can see what it looks like. And we'll put in that 2x, sorry, we'll put in x squared. Just have to go get my Mathematica. So we'll put in x squared plus 1. Okay, so there's a picture of it. And what I'm going to do is I'm going to try and put in the tangent line for you at the bottom at x equals to 0. So if I did that, I'd be at y equals 1. There's the tangent line. The slope is 0. And you can see that that's what the math told us would be, that picture would be. It said right here, it said that if you go to the point where x equals to 0, so if we go to the point where x equals to 0, we will have a slope for the tangent of 0. And if we look back at that graph that I just had up, that's what we should see here. That flat line is tangent and it's 0. Okay. So now let's find the other spot, which is at -1. So if I go to -1, then I'm going to be, let's see here, just going to get rid of one of these here. Okay, so this will be the line. Let me just see here. -2. So there's the tangent line, whose slope is -2. And you can see it grazes exactly one spot on the graph, and it's right here at -1 that we see it. So we could predict that before we saw the picture. It says here, if you go to -1, so if I'm looking at the point -1, if I put -1 in, the slope will be -2. That line we just saw had a slope of -2. So that's what we're trying to figure out here is, how steep will this line be that's tangent to the graph? Okay, that's what the process is that we're finding is a way to predict it without having to use the graphing calculator. That being said, your graphing calculator can do this. So what I'd like you to try is put in x squared plus 1 to your graphing calculator. And there's a function called draw. Okay, so you go second function and draw, and that'll take you to your screen. Option number 5 on my calculator anyways says tangent. So I want you just to set it up so that you can see, I'll come around and see that you have it working in your TI-83.